Here at Granta Design, I have the pleasure of introducing Claes Fredriksson.
Hello everybody.
And Claes and I will be running a webinar on electric cars, sustainability and eco-design. So, over to Claes.
Yes, thank you Hannah, and hello. Welcome to this case study session, which is based on another one of our advanced industrial case studies for EAG Pack. My name is Claes, as you've heard, and I'm responsible for the online training here at the Education Division of Granta, and I also run the workshops and short courses that we arrange all over the world. This is our fourth in our series of quarterly online training sessions for EAG Pack users. And today's topic, as you've heard, is a very interesting one, I think: sustainability and eco-design of electric cars. The philosophy is that these case studies should inspire, for example, engineering educators and facilitate the materials-related teaching that might occur in your universities. For this case study session, you've already heard Hanna-Emilia, and she's the product manager for EAG Pack at Granta Design. So she's very good contact if you have suggestions for improvements in the software, for example. Okay, so what's today's agenda, Hannah?
Good. So today we are going to start with an introduction of the case study, give some background on electric cars in general and also on EAG Pack. And then we'll be showing you how you can use the EAG Pack to compare different powertrains in the Eco Audit tool before moving on to visualizing data in the EAG Pack that's pertinent to batteries and looking at the critical materials used in batteries and powertrains in electric vehicles. We'll also have a look at the sustainability database and the information that we've got on regulations in the nations of the world. And finally, we'll look at the performance of electric motors and why rare earth elements are important.
Very good. Okay, so let me introduce the subject a little bit more. The background here is, of course, that we think that the development of electric and hybrid vehicles is a very interesting one that will engage and interest our students. As you may be aware of, there's a huge growth currently in the number of vehicles, both in the UK and globally. We have a diagram here showing the increase in the number of vehicles in the UK, but the development is the same, I think, in most European countries at the moment. It seems that the hybrid electric gasoline vehicles is the most popular one, but there are also a great number of electric vehicles being sold. So with the electric vehicles, of course, comes the need for batteries. And traditionally, many battery types have been problematic in that they contain toxic or otherwise environmentally unfriendly elements. So in most car batteries today we have lead, for example. There's also nickel-cadmium based batteries and old type of batteries that contain mercury, and all of those are problematic for health or environmental reasons. So they're being phased out. More modern batteries are typically based on lithium-ion technology, and they also quite often contain cobalt in the cathodes. So that is considered a critical element, so we'll talk a little bit more about that. Most electric motors also have magnets. Now, the early models of Tesla, for example, they had a technology based on induction, so they were more or less magnet-free. But even Tesla has, in their more recent models, started to use a kind of very strong type of permanent magnet to increase efficiency in the electric motor. Now, these very strong magnets do contain rare earth elements, and they're typically based on neodymium and may also have samarium, for example, and dysprosium, which are all examples of critical elements. So we'll mention that towards the end also and have a look at why they are needed in the electric motors.
Good. So we are going to first have a look at different powertrains for electric vehicles and do a Eco Audit of those. So the Eco Audit tool, you might already know, is a tool in the EAG Pack that is there to help students to look at the environmental impacts of a product over its whole life cycle. So from the material production right through to manufacture, product use and end of life. And it looks at the energy used over that life cycle and also the carbon footprint. And it thinks about the feedstocks, what's an energy used in production, and also how the product is transported as well. And luckily in the options already available in the Eco Audit, you can choose a family car or an electric family car within the mobile mode when you're thinking about the use phase of a product.
And that's lucky, because we will try to use that in today's demonstration. Let me go through the workflow so you understand what the different steps are, and hopefully you'll be able to reproduce these at home. Now, if you want to find out about details, numbers that we put in and so on, these will all be available in the case study paper that will be made available next week after we have broadcast the rerun of this session. The next slide after the workflow, I will look at the result of the Eco Audit and show the main features of that, and then I will actually go into EAG Pack and show you how you can achieve a result like that. We will study 4 different scenarios, from gasoline engine, which is an internal combustion engine, ICE, all the way to a fully electric vehicle. And we will have 4 scenarios, and in the case study paper I mentioned, these will be called number 1, 2, 3 and 4. And in order to make these Eco Audit projects, we will use a little shortcut, because in EAG Pack we have embedded some project files already, and family car is one of those. So I will show you how to retrieve a family car bill of materials that we'll work with, and then we'll use that to modify and study the different powertrains. We will use gasoline as the reference car, and then we will add on the other options in the comparison. So on the screen at the moment you can see a couple of things that you can do with EAG Pack. You can start with the embedded bill of materials, and you can make small modifications very easily to fit your specific needs. In this case, for example, I've modified the bill of materials with the weight of aluminium here, or aluminum. So I've reduced the aluminum to make it more similar to a mid-size car that we'll use in today's comparison. Other things that you could do to your bill of materials is that you can put in different options for transport, for example. And in this case, we will look at a case of an electric car or a hybrid car produced and delivered in Europe. So we'll put the country of use to Europe. And just as an example here, we have put in a transport of 1,000 kilometers from the factory out to the different retailers. So that's one step. And then we're going to use the compare with option in the Eco Audit to make copies of this bill of material and to add on materials for batteries and make the adjustments necessary to be able to make this comparison. So hopefully you can follow that and see how easy and good it is. Right, so the result that we expect to get is something like this one. Now you may have a different set of colors in your version here, but basically we have the 4 different scenarios here that I describe. The first one to the left here, number 1, is the gasoline reference car. And we're looking at the energy use here over the different phases of the life cycle, plus the transport. And I have included here some other information. We have all the different options for the mobile mode here, and they contain gasoline family cars, as you can see here, and they also have the options for electric cars here, and even the hybrid gasoline electric car there, which then represents the sort of average or typical energy consumption per kilometer and per kilo of the use of the car. Now, if you take that into account and you try to mimic the different types of cars, you will get this result. So the fully gasoline example reference car will have a low material consumption in production. Very little energy is spent on the manufacture of the car and the transport, but the main energy will come in the use phase. So we see here that this is the dominant component in the Eco Audit. If you put in a hybrid car, such as the early Toyota Prius, for example, you will have an increased energy cost in the material phase here, because they contain a larger battery, for example, and they have electric and gasoline options in the powertrain, and therefore this one is a little bit larger. However, they are more efficient in the use phase, so we can see a reduction of the energy in the use phase here. The third one is a plug-in hybrid, which is a more modern way. It means that you have an increased battery capacity, so you can actually top up or charge your car, and then you can run a certain distance on pure electricity, and then let the gasoline part kick in when needed. And even if you're using gasoline, it will have an increased efficiency, like the hybrid example. So the overall result here, as you can see, is that increased battery will need more material energy, but it will reduce the use phase a little bit. And finally, I will show you how to put in an example of a fully electric car, which reduces the need for a gasoline engine, obviously, but requires much more battery. So the energy use in the material phase here is greater, but at the end it will take less energy in the use phase. So I'll show you how to make all of these entries into the Eco Audit, and then you can use these as a base of discussion in your classroom. Now, the data that we need for batteries and energy needs and so on, I have got from Volkswagen Golf, which provides a good starting point, because they have the full range of vehicles. They have petrol and diesel vehicles, and they also have a fully electric vehicle, which is the e-Golf mentioned here, and they have a plug-in hybrid version, which is the Golf GTE here. So some of the data that I will be using is taken from this as an example, but of course, as usual, you can put in any data that you have found or that you think is relevant. In our case, the plug-in hybrid has a battery weight of 120 kilos, whereas the fully electric Golf has much more lithium-ion batteries and a total mass of 318 kilos, which I will be putting in. Okay, so I will leave the slides and start up EAG Pack, and hopefully show you exactly how you do how you can achieve this kind of result. So I'm starting up now 2018 version of EAG Pack, and I will be using the level 3. As you can see here, I have access to all the different editions of EAG Pack, and you may not have that, but I will be using today for the maximum maximum number of data and tools, I will be using the level 3 sustainability database. So to get the sample file, I will click on the Eco Audit, and from within the Eco Audit I will then open project files. So on your local disk, you go to the program files x86 and you find the folder where the EAG Pack is installed. And in this one you have a number of important folders. One is called samples, and in there you will find the Eco Audit project files in English and French, and we will use the English version. So here you see all the embedded project files you have that you can use in your teaching very easily. Now we'll be looking, since we are in level 3, we'll be looking to use the family car here for level 3. So I will open up this one, and it'll give me a warning because this file exists both for the Eco Design edition and the Sustainable Development edition. They are basically the same. They both have the enhanced Eco Audit, so I can just click OK for that one. And then I promised that we would tailor this bill of material a little bit to fit our need. And what we need to do is to adjust the total weight of this one, because this one is an older model of car, and it has a large gasoline engine. So what I will do to make it simpler and more realistic for a mid-size car like the Volkswagen Golf that we will be contemplating, I will simply reduce the amount of aluminum in the engine here. So I will take away 200 kilos and put a more realistic weight in there, which leaves the total weight here somewhere just above 1500 kilos, and that should be good for our purposes. Now we need to put in a few more details. We need to tell it what kind of transports are involved, and as I mentioned, I will add something to cover the transport from the factory. Now, Volkswagens are made in Germany, so we can put a transport from Germany to somewhere in Europe. Now I'm not sure exactly what kind of vehicle is used here, but as you will see, that this does not matter greatly. I will choose this example, the 3-axle truck, 26 ton, and I will put in a distance of 1,000 kilometers just as an example. And thinking about Germany, you can reach large parts of the European market from Germany within the radius of 1,000 kilometers. We also need to put in some details about how it is used. So I will keep the default values for the product life, 10 years. But I will, since we produce and deliver this to Europe, I will put the European energy mix in here. We will use the mobile mode, as we mentioned before, to mimic the transport with a car, the mass-dependent transport of a car. And as you can see, it's already set for a gasoline family car there, with some a small but typical sort of usage here, 250 days per year, and a moderate use of 100 kilometers. And this, of course, you can change as you want. Now, if we click the summary chart there, we will see the energy that is being used over a product life like that. And you can see here that the material is the second largest energy consumption, but the manufacture and transport here are very low in comparison to the use phase. So 10 years of use phase will consume quite a lot of energy, and that can be seen there. Now I want to add the 3 other powertrain options. So I will do that by using the function which is at the top of the product definition here. I will use compare with, which bases the next entry on the existing bill of materials and the transport that I put in. So I will ask for a copy of the current product, which gives me here in the summary chart, as you can see, an exact copy of the gasoline car. And all I need to do now, in order to put in a hybrid example, is to put in a little note here that this is the hybrid gasoline electric vehicle, and this is of the Toyota Prius, early Toyota Prius type, which means that it is still a gasoline car, but that it has an electric part in the powertrain, so it is more efficient. But you cannot charge this with electricity from the grid. So this is a hybrid option. Now we need a little bit of battery added to the mass here. So I will go directly into the bill of material and keep all the car data there, and then put in a hybrid battery. And I will show you now something that's quite interesting. So we don't have to put in the lithium component here, because we have components. We have electrical components as an option for the Eco Audit. And if you open up the folder for electrical components, you see here that we have a folder of different types of batteries that we have put in. Now in this case, the early Toyota hybrid vehicles had nickel metal hydride batteries. So I will take and add 42 kilos of this one, which matches the Prius, and that's what we need in order to make the bill of material more realistic. Let's keep the delivery here the same, just for comparison's sake, but of course if you have your own data you can put that in. And in the use phase, it's no longer a pure gasoline car, but we can use the data we have for a hybrid gasoline electric family car, and that will take into account the greater efficiency that you have in the powertrain of a hybrid car. Okay, so when you've done that, we have here the first part of the comparison. We have an increased material use because of the increased battery, and we have a reduction in the need for energy in the use phase. So overall we can see here that we have a considerable energy reduction. And we can continue now to try to put in data that mimics a plug-in hybrid. Now we don't have plug-in hybrids here as an option, so we will have to design our own input. I will use the Golf GTE as an example, and I will create another comparison based on the hybrid vehicle. So let's see if we make another copy of that one, and we will have to rename this one into a plug-in hybrid. And the Golf here has a different kind of batteries, and it has more of it. It still has the same engine, or a similar engine to the gasoline one, but it has significantly more of a lithium-ion battery. And the best match in our database for this option is this one here, the lithium-ion rechargeable battery. So I will put that one in, and I will use the actual mass from a Golf GTE, which is about 120 kilos. We also need to take into account here that the range of a plug-in hybrid Golf is not fully 100 kilometers. So we need to reduce this to 50 kilometers, which is, I think, quite close to the actual range they say in the Golf advertisements. We can keep the gasoline hybrid because the efficiency of the powertrain will be similar, but we need to add a component here mimicking the energy losses when you charge the car. So the electric 50 kilometers here will be run on a European energy mix, and I will put in here a typical data to charge the plug-in hybrid car so it can reach about 50 kilometers. Here we have options to cover the energy conversion, and as you can see here we have an option for electric to chemical when it comes to advanced batteries, so that will be the one that's most accurate. From your household grid electricity, it's difficult to, unless you have three-phase equipment, to take more than 2 kilowatts, so I will put 2 kilowatts. And if you remember the data I showed you for the Golf GTE, it has just over 8 kilowatt hours of capacity in the battery, 8.7. So I will say that we're charging this car by 2 kilowatt hours of power every day that we need the car, so for 250 days per year. And to fully charge the battery we will need something like 4 hours. And then again, this is a rough approximation, so if you have accurate data, please put that in. I am making this comparison just as a platform for discussion, so I'm putting in some typical and rough values, and I don't expect the values to be the complete accurate ones. But as you can see here, with this combination of data, we achieve a summary chart that shows you the trend. More lithium battery requires more energy in the production of the material, so the material phase is increasing here, and the efficiency is a little bit higher, so it means that the total energy use will be lower with this combination of data that we have here. Now for the fully electric one, it is a little bit tricky. So we have two options. I will again add the number 4 in the comparison as a copy of the plug-in hybrid version, and you can see here that it adds on a fourth contribution to the Eco Audit. As you could see, looking at the Golf, it has a much higher capacity of the batteries and a much larger range. So I will put in the actual mass of the lithium-ion batteries that they declare in their product specification, which is 318 kilos. And this time we have gotten rid of the engine. We no longer need the engine, and the engine block in a Golf can weigh as little as 100 kilos of aluminium. So in one of their versions we can remove 100 kilos of aluminium there for simplicity, so I replaced the 238 with 138 to mimic that. And then we need to modify the use mode here, because the fully electric car has a range that can cover the full distance of 100 kilometers here. If we do that, we need to of course adjust this one to a fully electric car as well. Electric family car. Yeah. So now we see that the total gain in energy we have is a little bit higher than in the plug-in hybrid version, and we should call this the fully electric one for the comparison. So let's call this fully electric. Now this data here takes an average use per kilometer and per kilo for an electric car. However, if we want to compare it with the plug-in hybrid case here, we might want to see what happens if we take the energy losses associated with the charging of the batteries. So we have that possibility here. We can, instead of using the average data there, we can switch over and only consider the energy used as the energy acquired through the charging. Now to reach a range of 100 kilometers, I'm simply going to double the charging here, so that's a very rough estimate, but thinking that we have a 2 kilowatt of facility at home. We should be able to reach 100 kilometers of range by putting in an 8-hour charge there. And we see in this case that the energy consumption goes up a little bit compared to the using the mobile mode here, and that's because it includes the energy losses here in the charging procedure. Now, of course, if you have more accurate data, if you know exactly how much you charge your car, then you can put that in. Here, the purpose is to discuss the result here and see that the fully electric car, doing an eco audit and looking at the energy used over the lifetime of the battery, we see that the lithium-ion battery does require a lot of energy in the production, but that you can reduce the energy need in the use phase considerably. And in our case here, the reduction is very similar in all these three cases. Now you may think, and I know we have some Norwegian customers on the line here. Norway is of course pioneering the use of electric cars. So for them this is an area of great interest. Now the energy mix in Norway is way superior to the energy mix you have as an average in Europe. So let's look at the carbon emissions instead of looking at just the energy use here. And that's another thing you can do in your classroom very easily. So with the final version here, the electric car, say that we want to study, instead of the energy use here, we want to see at the carbon dioxide emissions. In the Eco Audit, there is a relationship between the energy used and a rough estimate of the carbon emissions. And as you can see, the pattern is exactly the same using fossil energy from the European energy mix. Now, if we go and look at the case of a country with much more renewable energy, in the case of Norway, of course, they have lots of hydropower to generate their electricity. And Norway is indeed represented here in the list of countries. So if we put in Norway there, you see that the energy use is still the same, but the carbon emissions have gone down to a minimum, and it leads to a much lower total energy consumption than if you charge it on a different energy mix. And this is of course the greatest benefit with electric vehicles. If you have an electric vehicle, you should make sure that you run it on renewable energy to maximize the environmental benefits.
So we should all move to Norway?
I think so. It's a great country. It's a great country. So just to finish off, I have shown you these two things, what happens if you look at, instead of the energy use, the carbon footprint for the European mix, and what happens if you want to study different kinds of energy mix, the effect of, for example, being in a renewable situation like Norway.
Mm-hmm. Great. So moving on to thinking about those batteries. So the batteries need to be light enough that we can transport them around, and also to be small enough so that we can fit them into the car without making the car much bigger. We're going to look at, in this slide, on specific power and specific energy. And you can see we've created this chart here using the energy storage data table in the Sustainable Development Database. And you can see that the lead acid battery is here, nickel cadmium is here, and lithium-ion batteries perform very well on both of these criteria. So specific power, the power per mass, is what we need to make sure that we can accelerate, and the specific energy is what we need to make sure that we've got a car that can get to the next charging point.
As a teacher of mechanical engineers, I find it quite interesting. In our database here, we have not only electrochemical energy storage, but we do have a few mechanical ones as well, and other types. So supercapacitors, you can see there, flywheels and springs, and even compressed air is there for a comparison. So that's quite good for a classroom situation, I think, as well.
Great. Good. So, and if we go on to another criteria, so we're interested in the volume of the battery, and if we look at the energy density, so the stored energy per volume, then again, lithium-ion batteries come out on top. You can see that lithium-ion batteries come out on top, but we have to think about it in terms of its criticality. So lithium is a critical element on the US critical elements list. And lithium batteries usually also contain cobalt, and cobalt is a critical material for both the EU and the US.
Yes, and if we want to elaborate on that and sort of have a reality check here, I've listed some of the actual cathode materials that are used in current battery systems. So I've listed a few of them here with their references, so you can have a look. The most popular or important one might be this one, which is a lithium nickel manganese cobalt oxide battery. And what is interesting in this sort of display is that the amount of lithium is actually quite small. So it's only about 1% or a little bit above 1% of this battery type that is the lithium. Of course, lithium is the charge carrier here, and lithium is one of the smallest and lightest of the elements, so that's the reason for that. But we can see here that the amount of cobalt is considerable. So it's 8 or 9% of cobalt in this particular type of battery, which makes it a little bit problematic, as we will see soon. So although it's only 1% of lithium here, we can see that the battery industry presently has a share of around 50% of the demand for lithium and also for cobalt in the world. So the batteries are already putting a lot of pressure on the resources. Here we have another clarification of the popularity of that type of battery here. Why is that the most interesting or popular version? Well, one reason is that it has very good overall performance. So here we can see a summary of the kind of performance that we can see, both in terms of specific energy and specific power that we looked at before, but also the other kind of performances, the cost performance and safety and so on. So this type of battery is a very good option in the real products later on.
Good. And as we were speaking before about the critical materials of lithium and cobalt, we can explore these really easily using the Sustainable Development Database in CES EAG Pack. It has information not only on materials and processes as usual, also on the elements, on energy, storage, and on legislation and regulation, and also on the nations of the world. And I'm going to do a demo to show you that. So we were interested in lithium-ion batteries. The first thing that we could do is to simply search for batteries. Yep. And there are legislation related to that, and we'll look at the battery directive. And this is a very basic summary and a link to the actual directive so that you can get more information. And at the bottom of the record here, you can see links to the elements and materials and nations of the world and energy storage which is related to it. So if we decided to go into, for example, the materials universe and have a look at the lithium, so we'll we'll just type in lithium, and I'm going to have a look at commercially pure lithium. So I'm going to scroll down to there, and here's the record for commercially pure lithium, and we can scroll down and see the usual physical, mechanical, thermal, electrical, etc. properties. But also down here we've got a section on restricted substances and risk indicators, and also critical materials risk. And if we scroll down, we can also see the main mining areas for this material. And you'll see that the United States has relatively little lithium compared to China, for example. And we can also think about the element itself. So if we scroll down and click on elements, so in the elements data table you have all of the properties that you would expect in terms of the atomic structure and crystal structure and so on. But you also have this geoeconomic data, so you can see the abundance in the Earth's crust, the main mining areas, and the critical materials information. And here you can see that it is not on the EU critical list, but it is on the US critical list indeed. What we can also do within the elements database is go to cobalt as well, as that was another element that was important in our batteries. And if we click on cobalt, again you have the basic information about the element, and then the geoeconomic data, and you can see where most of the cobalt comes from in the world, which is the Democratic Republic of Congo. And you can see that it's on the critical materials list for both the EU and the US. So let's go and explore the Congo and figure out why it might be on those critical lists. So we can go to the nations of the world that mine this element and click on the Democratic Republic of Congo. And again, for each nation we've got some basic information about the area of the country, where it is, all of that kind of stuff. Information on people, education, and then there's an area on human rights and good governance. And you can see here that there's an ongoing conflict in this country, that the rule of law index is very low, control of corruption is very low. So if you're sourcing a very important element for your product, mainly from this country, then you might want to think again. Good. So I think at that point we go back to our presentation.
Yep. Let's see. We're almost out of time. I'm going to go very quickly through the magnetic performance stuff that we have here in the database. And if you want to see the details that we have used today and more information about background and so on, I recommend that you have a look at the case study paper that we will be publishing on our website. Very briefly, if you want to look at magnetic performance, and of course that is a key aspect of the performance of the electric vehicle itself, the electric motor. There are two factors that are important. It's a combination of intrinsic coercive force, which represents how difficult it is to demagnetize a certain magnet. And then you have the remanent induction, or the remanence, which sort of represents the strength of the magnet. And you want both of these values to be as high as possible. As you can see in this chart here, that you can easily make from within the magnetic data table of the database of level 3. We can see here that we have a few magnetic polymers in here. They don't perform terribly well, but they may have other strengths. I have highlighted in yellow here the ceramic magnetic materials. They're also very medium performant. We have samarium cobalt based magnets, which are a bit better here. And we have at the top here, this group of magnets are all neodymium based magnets, and they are the best performing, and therefore they are most widely used for high performance applications. Now in EAG Pack you can look at not only the intrinsic coercive force and remanent induction at room temperature, but you could also go into the temperature dependent properties. And I think I will open up and quickly show that to you. But the conclusion is that at high temperature, and of course we're talking about automotive applications here, so the temperature, especially in plug-in hybrid cars and in hybrid cars, might be quite high. So at 100 degrees, for example, we no longer have polymer or ceramic options here, but it will be the neodymium magnets that dominate. For example, this neodymium here, N40SH, is a good one, has both good values for the remanence and for the coercive force. I wanted to open EAG Pack very quickly just to show you where to find this data. So if we go into the sustainability database and we look at magnetic materials, we have hard magnets, which are high performing, and soft magnets. Let's look at the hard magnets. We have polymer, metal and ceramic. Let's go into the metal ones. We have different types here, and we have folder level records for the information about the neodymium ion boron type magnets. And as you can see here, it has a lot of explanations about this type of magnets, its limitations and so on, and a key to the names of these magnets, which basically reflects the temperature that they can endure. So the SH one we were looking at is good for up to 150 degrees. You can see also the composition here of a typical neodymium magnet. So neodymium is not the largest part of the material. It is actually still an iron-based material, and to endure the high temperatures, you have added dysprosium here, for example, and praseodymium there, and there's also some cobalt in these. All right, so if you want to get in and see the details of this magnet, let's look at that one, for example, the 40SH. You can see here that it contains the composition, a lot of thermal and magnetic data. Here are the temperature dependent properties that I mentioned, that is embedded in the plot. And you can set the parameter here to reflect room temperature, or you can change this value to 100 degrees, for example, to mimic the situation in an electric car. Here you can also see the BH curves, which are important when you look at the performance of the magnet. And then other important information about the critical materials risk. So if we want to look at the criticality of these rare earth metals, we can see that the geopolitical risk level and so on, the price volatility is very high. And the one reason for that is that it's predominantly produced in one country, and it's China. As we can see here, they dominate the main mining areas for these materials, and that may be one of the reasons also that they are considered critical both in the EU and in the US. Okay, I think let's finish off here.
Yeah, so we're running out of time. I hope that you've enjoyed this case study, and that you've seen, that this really relevant topic of electric cars can be tackled using the EAG Pack with the Eco Audit tool and the Sustainable Development Database that's got lots of good information on here. I want to thank you for attending this meeting. Well, thank you very much, class. It's a brilliant case study. As class said, so we'll be making the actual paper, a very detailed paper, available next week. We'll also work on cleaning up this video into a really nice recording for you so that you can watch it at your own pace, and other people you can share it with other people that you think might find it interesting. And also classes slides will be available, so have a look for an email coming your way that gives you details on how to access that. Great, thank you very much for attending. Bye for now.
Thank you very much. We'll try to answer your questions afterwards in private.
Okay.
Bye-bye.
Bye.